Actually, I'm not. Sorry. Yep. So now I'm recording. Thank you very much for checking with us, because that would have been disaster. Yeah. Now it is recording, isn't it? Yeah. So I'm going to check once more that I'm recording. Whoops. Okay, let me check. Yes, it is recording. Okay. Okay, so we checked how fast is this implementation of Vegas algorithm when we use this speed up, the two speeds up, which is by Numba and by vectorizing the calls, and we saw that actually this increase in speed was enormous. All iterations are done in no time, and the result is within statistical error the same. So this is great. And now the homework that we assigned for the next week on Wednesday is the following. So I want to ask you to generalize the Vegas algorithm so that the integration limits are given by an arbitrary number from A to B. So up to now, we were always integrating from 0 to some number, which we called unit. In actual integration, it was pi, 0 to pi. But right now, we need an arbitrary A to B, and it's going to be tested then on numbers between minus pi to pi. So you can still assume the supercube in which all dimensions have the same limit. I mean, in principle, we could generalize the algorithm in such a way that A and B for each dimension is different, doesn't it? So it's generalized hypercube, which has a different shape in every dimension. But I mean, at least for the things that we're going to do here, this is not necessary. So we're going to avoid this most general case. Although the change is not complicated, it's easy. Then once we generalize it in this way, we can test on the same function, but taking the limit from minus pi to pi instead of from 0 to pi, which of course will result in 8 times larger integral, because we have 3 dimensions, and the value should be twice as big for each dimension, which is 2 to the power of 3 is 8. And then finally, I want to ask you to speed up the part of the code that redefines the grid using, I didn't say explicitly here, but I'm going to solve this with Numba. So Numba is good enough for our purpose. Yeah, so this is the first part. Then the second part is going to be generalizing Vegas so that it works for complex functions. And then once we do that, we are going to test it, this generalized complex Vegas, with this following function, which is actually a polarization function for the uniform electron gas. I'm going to spend a few more minutes on explaining this particular set of parameters that we choose here, so that you're going to be more familiar with this. But let me first solve this first 3 bullets that we have here. So the first part, it doesn't need to rely yet on the polarization function. Okay, so here's the solution. So I wanna well, let me first clear all the cells, all output, clear all. Okay, let's start from scratch. First, I want to import Numba, because let me also restart the kernel, because that makes sure that I don't have anything in memory from the previous inputs. Okay, so first we are gonna import Numba, and now the cumulants for now are exactly identical to what we had before. There is no change here. Eventually, when we generalize the code to an arbitrary array with respect to frequency, as required by the very last bullet in here, so the very last bullet, which is optional, we're going to need to generalize this algorithm to an array with frequency. At this point, cumulants will get changed, but for now, not yet. So I just copied literally from the previous exercise, this cumulants. It's the same thing. So then we said that the important part that the homework is this, how to refine the grid. So my solution is the following. I take the grid class exactly as it was, but then I would need to speed up a member function refine grid. And it turns out that speeding up member function with Numba, it's not straightforward, because you would need to basically change the entire class into Numba class. It's possible, there's documentation about that. I tried, and there were several issues that I didn't have patience and time to resolve. So what I decided to do is very simple. I'm going to still use the same class, but I'm going to define a function inside the member function refine grid, which will do all the work. Okay. So this refine grid underscore will do all the work, and it's actually just a simple function. Okay, the simple function, the refine grid, needs only the function imp, which is basically projection of our function on all axes, and then it also needs the previous grid. So imp is the function with which we're going to construct the new grid, and self G is the old grid. These are the only two things that we need in order to do all the work. And now the defined grid is actually almost literally copied from previous class, except that right now is just a simple function. Okay, and it has as an input self underscore G. So whatever before was called self.g now became self underscore G. This is just my choice for the name of this variable. And then you can append this JIT or this Numba line, which speeds up the entire function. Yeah, very important thing here is that in Python, if you have an argument which is a simple variable, such as integer, complex, or floating point variable, then it turns out that it's called by value, which means that is not being changed. Okay. However, if this argument, such as self G here, is an array, a NumPy array, or any list, then it's actually called by reference for efficiency. I think we discussed this when we were learning about Python. So naively, you would think that if I give the self G as an argument to refine grid, then if I change self G inside refine grid, it's going to be changed also inside the class. That was my understanding. Okay, why? Because self G is not a simple scalar, but is an array. So if it was a simple scalar, then according to Python documentation, it's not being changed. It's called by value and not by reference. But if it's an array, then it's called by reference. So basically, when you change the variable inside the function, it's also changed inside the class. Now, however, it turns out that when you use Numba, it doesn't behave that way, which I was surprised. So when you use Numba, then it turns out that if you change self G inside the function refine grid, it will not get changed. Okay. Anyway, it's not a good idea to change it anyway, because this is not Pythonic. So the Pythonic way to do it is to return, rather than changing self G inside the function, is to return the entire array and then assign it back to self G. So this is anyway the preferred Pythonic way of writing functions. So basically, on the right-hand side, we just give self G as a read-like array. So basically, it's an array that you can just read, but don't change. And then we change the array self G only once we return from the function. That's anyway the preferred way within Python, and this works correctly. So therefore, inside the refine grid, before we were changing self G, now we don't change self G. Otherwise, the function is exactly the same as before. So this refine grid does exactly the same. Basically, it allocates the new array for the entire grid, which we call GNew, and then we fill in the GNew, and we just return GNew at the end. So we just return the entire array, and we don't change self G here. Okay, so self G is being changed only inside the class once returned. This works correctly. The alternative doesn't work correctly, and it's not Pythonic anyway. Okay, so therefore, speeding up this redefined grid is really simple. Once more, the only thing that you do is you define a function, a simple function, which is not class member, a simple function that does all the job. And then when you return the new grid, and you assign the new grid to self G. That's all. Okay, let's do that. Now, this smoothing of the function and all these things is identical to what we've done before. I just copied this thing to the new notebook, but I didn't change, so I'm not going to discuss that. And then, okay, so what else did I do in Vega step 4? Let me see. I think the rest of the steps are identical. No, actually they cannot be identical. We had to change the limits of the integration, isn't it? So before, the input here as a second argument was unit, which was the integration limit, upper integration limit, and we always started integrating at 0, but now we have to generalize this so that we integrate from A to B, isn't it? In general case, from A to B. So how do we do that? Well, only a few lines need to be changed. So one line is that unit dim, which is the volume, this is actually just the volume of the entire space, is now B minus A, isn't it? AB of 1 minus AB of 0, which I can call B minus A to the power of dimension, isn't it? So instead of unit to the power of dimension, it's B minus A to the power of dimension. So this is really simple. The volume has been changed right now. Then what else? This line has been changed. So basically, when we calculate G of X here, we evaluate it as a linear interpolation of on random numbers. So this X here is the array of random numbers, and we had to interpolate random numbers on this grid, G of X. And up to now, everything is the same as before. The big difference is that we have to then stretch this array which was defined from 0 to 1 to A to B. So basically, in this line, the g of x has to go not from 0 to 1, but from A to B. So how do we do that? Well, this is very simple. We set g of x times b minus a plus a. That's it. Very simple. Then we, of course, evaluate the function on this properly defined random variables, which go now between A to B, not from 0 to 1. And then finally, it's when we return very final value, we have to properly multiply with volume again, which is b minus a to the power of dim, which is exactly the same as this quantity that we evaluated in the top, which is unit dim. So these are the only basically 2 or maybe 3 changes that you need to do in order to generalize the algorithm that will work from generic A to generic B. Okay, so let me now evaluate this. Now my integrand is exactly the same as before. We didn't change anything. And now we are gonna test it. We are gonna do 2 million random numbers, 1, 2, 3, 4, 5, 6, yeah, 2 million numbers. So exact value is 2 to the power 3 times bigger, which is 8 times bigger than before. We have the same type of cumulants, 128 values for the grid points or number of bins for the grids. We are going to start with 100,000 random numbers at the very first step, and then every time the next step is being done, we're going to increase this by 5,000 points or 5,000 random numbers. The grid is initialized here, and then we do this. We call Vegas, but now with the limit from minus pi to pi. So this is crucial. We change here not from 0 to pi, but from minus pi to pi, and then we print out the result. So let's see. Yeah. So the function evaluation is very quick. I mean, the first time was maybe a little bit slower because we had to Numba had to basically convert this code into C code, but when you call it second time or the third time, it's done basically instantly. So you see the speed right now is incredibly fast. Now the result, how good is it? Well, it is the real error is more or less the same as statistical error sigma square, and the value is close enough to the exact value. Exact value should be 11.14, and the approximate value is 11.128, which is close enough to the exact value. Of course, when you run it again, we're going to get slightly different result. All of those results are close to sigma away from the exact result. So the code works. So this is the first part of the code and the first part of the homework. Now, if we plot the grids, grids G of 0, G1, G2, so all 3 dimensions, we plot the grids, we see that the grids now are different. So they are, actually, it's doubly repeated the grid from before, as expected, because we have a peak at minus pi, at 0, and at pi. As that. So before we had only peak from at 0 and at pi, therefore the grid was flat at the place where we have the peak, but now we have 3 peaks. So therefore there has to be another very flat region of the grid at the very beginning of the interval. So if your grid looks like that, then the code most likely works. Okay, so this was the first part of the homework, which is relatively straightforward, but the second part of the homework has to do with making it allowing complex numbers and then calculating polarization of the uniform electron gas. This is so-called Slingheart function, which gives susceptibility. For example, this is either charge susceptibility or spin susceptibility. And in the dispersion in this case is written in dimensionless units. So normally energy is k squared over 2m. Basically, we are dealing only with kinetic energy here. This is the lowest order in perturbation theory. Therefore, the interaction is ignored. So the dispersion is just k squared over 2m, but in dimensionless units, it's just k squared. But we subtract the Fermi level. So basically, or Fermi energy. So Fermi energy in this case is kf squared, where kf is the Fermi momentum. So the Fermi momentum turns out to be 9 pi divided by 4 to the 1/3 divided by rs, where rs is a unit of density, and we're going to take rs to be 2. Okay, so f is the Fermi function, then temperature is some small number. This delta, which is delta is broadening, is the small broadening, has to be even smaller than temperature, like 1 order of magnitude smaller than temperature. And then we're going to take the frequency to be 0, the momentum to be 0.1 of the Fermi momentum, which is more or less close to 0, or a very small number. And then we're going to do integration limits from minus 3kf to 3kf, which is equally good as minus infinity to infinity, because the functions are actually 0 outside this range. So, but let me explain how do we get to this particular set of numbers. So this is just a uniform electron gas, which is something that you learn in basic, I think, even undergraduate course. So the first thing to remember is that Rs is the average distance between electrons. So this is the volume of the electrons is 1 over the density, isn't it? If the volume is 1 over the density, that means that Rs measures the average distance between electrons, and it's just another way of measuring the density. So instead of saying that the density is some number 0.123, we rather say that Rs is 1 or it's 2 or something like that. Now all these numbers actually Rs is not in units of nanometers or angstroms, but it's in unit in Bohr radius, because it turns out that when you measure distance in Bohr radius and you measure energy in Rydbergs, then these units are very nice, and that's what we do here, isn't it? So everything is just like in LDA. We measure distances in Bohr radia and energy in Rydbergs. So once more, Rs is just simply related to density. Now the question is, how do we get Kf? I mean, why is Kf? I said Kf is equal to this strange number, 9 pi divided by 4 to the 1/3, 1 over Rs, isn't it? So where did we get this number? Well, this is a typical question for the undergraduate exam. So to count number of states in a Fermi system, isn't it? If you have a Fermi non-interacting Fermi system, then basically you know how many states you have, which is the volume of the in the K space times the occupation number of each of the states. And this occupation number in Fermi statistics is just a Fermi function. So all the states up to the Fermi level are occupied, isn't it? So this is basically is a step function. Well, at 0 temperature step function, otherwise it's a smeared step function. And we know that here this value here is Kf. Or energy is at energy EF. So like this. So in this 2, where is this 2 coming from? Anybody? Can you help me? I hear no feedback. Please, any idea? Where is the factor of 2 coming from? Are you following? Anybody following? Where are you? No? Factor of 2, where is coming from?
Spin.
Spin. Yes, thank you. Thank you. So factor of 2 comes from spin degeneracy. So when you have a Fermi system, well, physical Fermi system of spin-full electrons, there are 2 states per each momentum, isn't it? 2 states, but therefore factor of 2. Okay, so yeah, this is then the density, and well, if you evaluate this, you get this number, pretty trivial, and then this is equal to kf to the 3 divided by 3p squared. And so the density is kf to the 3 divided by 3p squared, but on the other hand, one of the densities 4 pi rs to the 3 divided by 3. Then from these 2 equations, you can simply relate that kf is 1 over rs, of course, and the proportionality factor is obtained from this simple relation between, well, so we take this, and you take this n here, and then you get simple relation between Fermi velocity and rs, which measure the density. So these are the quantities we need. And in addition, we also said that we need n of kf, which is the density of states at the Fermi level, because our final result of polarization at omega and at omega 0 and small q, it's known to be close to this value of the density of states at the Fermi level. Okay, so basically, in other words, to say this is the susceptibility of the non-interacting system is the density of states at the Fermi level. This is well-known result. Yeah, so what is the density of states at the Fermi level? Well, you just look at, again, this quantity here, but now you don't integrate over all d to the 3k, but only a shelf around kf, which is basically 4 pi kf square, which gives you 4 pi kf square, isn't that like a volume at the Fermi momentum divided by this 2 pi to the 3, just like before. And this turns out to be kf squared divided by 2 pi square. Now here, when we talk about density at the Fermi level, we usually don't multiply with spin degeneracy. I mean, this is convention, okay? So we might, but we might not, but by convention, this factor of 2 is left out. So that k and n of kf is defined as k squared by 2 pi square. Yeah, so okay, so the parameters that we chose here for this exercise is rs is 2, which is kind of a relatively weakly correlated system where this approximation is not bad. Then we take temperature to be relatively low temperature. So basically, kf square is like the Fermi energy EF, and the 0.02 is relatively low temperature. So it's only 2% of the Fermi energy, which is sufficiently small that it's a good representative of 0 temperature. Now the broadening is even 1 order of magnitude smaller than the temperature, so that basically this is a good representative of limit when broadening goes to 0. And then finally, we take 0 frequency, and we take small enough q, which is finite but small. And why do we do that? Because we know analytically what is the value of this quantity when omega is 0 and q is small. So it turns out that actually this limit is singular in the sense that the value of polarization as a function of omega q depends on the order of the limit. So here we take the frequency first to 0 and q later to 0. If we did the other way around, we will get a different number. So, so therefore our q shouldn't be 0, but should be small enough that we take the important limit of low frequency response. Yeah, so that's the formula that we're going to implement. And now we need to discuss how how the code needs to change. So we said that this quantity, this needs to work for complex result. Why? Because this quantity here is complex. You see, this I delta here makes the entire result complex. And of course, the imaginary part is very important. It's not just the real part, but also imaginary part. It's usually the most important part. Okay, so what do we need to do then? Well, we defined before the average of the function fw, and this is basically the quantity that measures the integral. So the integral is evaluated from this, and clearly this quantity needs to be complex. Now, on the other hand, the square of the function, which is measuring the statistical error, that is more convenient to be real, because statistical error is, we want to estimate it as a real quantity rather than the complex. And therefore, we're going to, instead of taking the square, we're going to take the absolute value square of this function for f square, because the idea is that statistical error is going to be a real number. So in other words, here we take the absolute value. Then this projections of the function, or basically this projection of the function from which we're going to construct the grid, it has to be real as well, because the grid needs to be real, isn't it? The idea of the grid is that the grid is real, so therefore the f twiddle has to be real, and therefore, because f twiddle is constructed from this f square, isn't it? F twiddle is basically constructed from f square, therefore f square needs to be real, and needs to be, we need to take the absolute value square, absolute value here. Okay. Finally, the sigma square is going to be generalized. Well, it's going to be kept in real, and the way to do it is, of course, taking this f squared real minus average value of f absolute value square, isn't it? So we take again absolute value to generalize it, and again it's going to be real. Then when we calculate average of function fw divided by sigma I squared, this is complex clearly, because fw is complex. Then the best approximation for our integral is complex, but here is wrong. So sigma square is actually real. Sigma square is real because the error is real. Yep. Finally, when we estimate chi, actually this is chi square. Chi square, this is being calculated in this way. So it's again generalized to complex numbers. We take the absolute value square rather than just the square. In real case, it was just square, but now the only difference is that we take absolute value square. Okay, so yeah, this is all we need to know before we start coding. Any questions so far? Everything completely clear? Any question? No? Okay, then let me continue. So we are solving the Lie-Vegas algorithm. Yeah. So the first part we want to do is to code the Slingheart function. So before we had just a very simple function, the simple function here, my integrand, isn't it? So instead of doing this my integrand, we need to return now more complex expression for the function value, which is given by this thing. So we need to do that. Okay. So the integration variable is just momentum k, isn't it? And the external variables are omega, q, and broadening, and I guess temperature, because we also need a Fermi function, isn't it? So once more, the input variable has to be omega, has to be Q, has to be broadening, and has to be temperature that is contained in the Fermi function. So how do we do that? Well, in my opinion, the simplest way to do that is to pack all these external variables into a class. I mean, of course, there are several ways to do it. One way is to work with global variables, but somehow this is not nice and it's not convenient. So it's better to pack them inside the class. NumPy usually solves this problem with args. You remember we said many times how to give args, additional arguments, to all the NumPy functions. I mean, that's another way to do it. I didn't do it that way. I did it through class. So this particular class will be, when it's initialized, we're going to give all these relevant quantities: frequency, Q, Fermi momentum, temperature, and broadening, isn't it? So this broadening here is this I delta, or basically delta, which is 2 × 10⁻³ kF square. Kf's Fermi momentum, temperature is given, is constant, and frequency is constant, and Q is constant. So all these things are going to be given to this class when we initialize the class, okay? And then the only purpose of this constructor is to remember these quantities, okay? Just to remember them. Actually, Q needs to be a three-dimensional array, so we're going to construct from a number three-dimensional array in such a way that the vector will point in z direction. I mean, this is completely arbitrary. It shouldn't matter. It could be pointing in any direction, but let's say that we chose that it points in z. The reason that it doesn't matter is because the system has complete rotational invariance. So any Q can point in any direction, and the result shouldn't change. But it has to be a vector, of course, because we're going to deal with vectors. Yeah, and the rest is basically we just remember all these input variables, and then we also compute normalization function value, which is 1/2π⁵. We pre-compute this in order to not compute this every time. So to remind you what this 2π⁵ is, this is the quantity that appears here. So 1/2π⁵. We're going to pre-compute that for convenience. It's not important, but we can do it. Okay, and then we define a call function. And when you define call function inside the class, as we discussed in the introduction to Python, this will make the class behave as a function, isn't it? So whenever you use class now as a function, this call routine is being used. And the input to this call routine is k, which is the momentum. And we need to return then the value of polarization function on this momentum k, isn't it? So therefore, the way to do that is first to initialize a proper array. We need to allocate it here. That's, I think, the best way is to allocate it before we go into the function. So we allocate the array, which has to be of the size of the momentum, isn't it? Because that's what Vega's algorithm needs. And now we need to make sure that this value is complex, not real, but complex. So this is very important. If we don't set the complex here, then we're going to truncate everything to real numbers, and it's not going to work properly. So this has to be set to complex. And then we are going to use the same trick as before to speed up the grid redefinition, redefining the grid. We are going to do the same thing, namely, we're going to create a function, which we call Slingheart inside, that will do all the job. And this function is going to be speed up by numba, isn't it? So basically, Slingheart inside does all important work and can be speed up with numba such that it's actually written in C at the lowest level. But of course, this Slingheart site needs lots of quantities which are being stored inside the class. So the class Slingheart contains all necessary information. For example, the frequency, knows the frequency, knows Q, knows KF, knows temperature, knows broadening, knows normalization, and also knows this, well, it gives the current, current place where we're going to store things, okay, so that we don't allocate this rest twice. So I think this is probably slightly more efficient. Okay, so then Slingheart inside basically contains all the important algorithm. So we go over all three. No, just a second. X shape of 0. This is we go here. We go over all random numbers. So the X, of course, is an array of random numbers, which is n times 3, isn't it? 3 is n dim, isn't it? N times n dim. So therefore, we have to evaluate this for the entire batch at once. So X is basically the same as K in this case. Okay, so what do? We unfortunately, we cannot do this all at once. Therefore, we are iterating over the entire batch, which is slow, but therefore we use NumPy to speed it up. We take one moment at a time, K, one at a time, momentum. Then we calculate momentum square minus Kf square, isn't it? That's as we discussed, this is what epsilon k is. Epsilon k is k square minus kf square, isn't it? So how do we calculate this k square minus kf square? Actually, here is k square minus kf square. How do we calculate that? Calculate it? Well, we can use norm from linear algebra. So I mean, in NumPy there is linear algebra package which contains norm of k. So norm of k is the usual length of the vector, isn't it? It's kx squared plus ky squared plus kz squared square root. So we calculate k squared minus kf squared, and the same we do for k minus q. So again, k here is a three-dimensional vector, q is three-dimensional vector, and k minus q is three-dimensional vector. So we use NumPy to calculate the norm of the vector, k squared minus kf squared. So this gives you the energies. Then once you know the energy, you can calculate the difference of the Fermi functions. So the important point here is that when you evaluate the Fermi function, you have to divide by temperature, because as you remember, the Fermi function contains energy divided by T. Now, the Fermi function itself, the way we code it here, is that it does not include temperature. So basically, the temperature enters through the argument. So it has to have Ek divided by T. And the important point is that the Fermi, well, first we make Fermi function fast by NumPy. And it's very important to have an if statement here, because this temperature is very, very small, and the energy can be relatively large compared to the temperature. So energy being a few hundred temperature is a few hundred times temperature is completely normal. It happens all the time, and we can get an overflow. So it's actually very common to get an overflow when you calculate the Fermi function. So therefore, we need to make sure that if the value of the argument is way bigger than 700, which is the limit on which you can calculate exponent, then we need to immediately return 0. Otherwise, we evaluate the Fermi function in the usual way, 1 divided by exponent to the x plus 1. Okay, so again, this is important so that you don't get an overflow. yeah, so the Fermi function, then again, it does not contain temperature, but therefore we need to take when we evaluate it, we need to divide energy by temperature. And then the result is very simple. This is basically -2 divided by 2 pi to the 3, the difference in the Fermi functions, divided by omega minus epsilon k plus q plus epsilon k plus I delta, isn't that broadening times 1j, 1I. So this is literally implementing this function, isn't it? That's what we just did. Okay, including this 2 pi to the 3, including this -2, and this function, this quantity. Okay, so this is this. We set it into rest, and then we return this result, and then this final result is being returned by Slingheart inside. Okay, so we evaluate this function. Now, the best way to test whether this works is to test it on a very small case. So we then, let's say LH is Slingheart, like this, Slingheart, and then we need to give all the arguments that initialization needs, isn't it? So of course self is kept, and then omega, let's say, is 0. Then Q, let's say, is 0.1 times, yeah, let's say the KF right now is just a number. I can always do that if I want to. I can say that KF is 0.1, let's say. Then Q is 0.1 times KF, let's say. Then I give KF, I get temperature, which is 0.02 times KF, let's say, and broaden it, let's say, 0.002 times KF. Okay, and yeah, so now I defined the class, but of course I didn't call anything yet. And then if I use class LH as a function, I'm supposed to get the correct output. So now I'm testing this call function. And in this case, I need to give as an input random numbers, momenta, which has to have, which is a two-dimensional array with n and dim. So n can be, let's say, 3, and dimensional is 3. Random, yeah. So there is it seems like an error, but that's not a problem. The issue is that we did not include from NumPy import random, so it doesn't know what random is. Oops, random, just a second, random. Oops, just a second. What is the problem? Now I'm confused. Random from NumPy import random. This should work. From NumPy import random. Random. LH of X. Oops. Yep, this works. I don't know. Probably misspelled something. So yeah, so here we define, let's say, a batch of size 5, but these quantities are three-dimensional vectors, so we have 5 times 3, and then we test that this Slingheart function contains returns correct polarization, which needs to be a complex number, and it needs to be it needs to return as many complex numbers as the number of values in the batch. So in this case, we said 5, so we get 1, 2, 3, 4, 5 values. If we give 10, then we could get a batch of 10 values as an output, isn't it? So this Slingheart thing works, at least returns correct dimension and has some numbers here that are not too crazy. And now the question is whether this when we use the Slingheart, when we use the generalized Vegas, whether it gives correct result. So we specify RS is 2 as required the homework. Then we calculate the Fermi momentum with this formula which we derived, which is 9 pi divided by 4 to the power of 1/3 divided by Rs. So again, this value of Kf is 9 pi divided by 4 to the power of 1/3 divided by Rs. That's something that we derived. Then this is the number of states at the Fermi level. Again, something that we derived, Kf divided by 2 pi square. Then temperature, we said it has to be 0.02 of Fermi energy, or Kf square. Broadening has to be 0.002 Kf square, we said, and we take cutoff to be 3 Kf. Okay, and we decided that omega is going to be 0. I call it 0 times Kf square, doesn't matter. Omega is 0, and Q is 0.1 Kf. So again, all these quantities are as required by the homework. Okay, now we need to set n dim is 3, of course, because we still have just three-dimensional integral. Now now we need to define how many functional evaluations we need to have, and how many evaluations at the beginning, and how much to increase. So I decided to take the final step. I'm going to use 1, 2, 3, 4, 5, 6. So it's 10 million at the end. But right now I divide this by 4, which is, instead of 10 million, I'm going to use only 2.5 million, I guess. So therefore the n start and n increase is going to be commensurately reduced. I initialized the cumulants, I initialized the grids, I initialized this Slingheart class, and then I give this Slingheart class instead of the function, isn't it? Because Slingheart class behaves as a function. And then the limits for the integration is between minus cutoff to cutoff, isn't it? And then we have to give the rest, maximum number of function evaluations, and number of steps, a number of random number of evaluations at the beginning, how much do we increase, how do we change the grid, and so on and so forth. Okay, so we are testing now Vega's algorithm, and it's pretty fast, even though it needs to evaluate this Slingheart function. This was with maximum number of evaluations is roughly 2 million. Then if we print the final best approximation for the integral is cum average, and if we define this by the Fermi number of states at the Fermi level, this should be close to -1, because the statement is that P of omega 0 and small q should be close to -nf, isn't it? So if we if we divide the integral by nf, we should get close to -1. And indeed, when we print this, we see that the value is -0.098 and something. So it's not exactly -1, or basically within statistical error is not -1, but it's close to -1, so 0.09.8. That's because q is not exactly 0. So if q is exactly 0, it would need to be exactly -1. But for finite q, it's slightly less negative than -1. Now what you see in the grid is interesting. So grid here at the very end, close to cutoff, goes extremely fast up. And the reason for this is because the integration limits are too big, in the sense that there is nothing going on at 3 kf. So if we reduce the cutoff to maybe 2 kf, then this sharp rise would be smaller. So this huge rise is because we take large cutoff. So we could take way bigger cutoff if we wanted to, and sooner or later, Vegas algorithm will eliminate all the points, or will basically optimize our grid in such a way that all the points which fall off outside the volume, which where function is finite, will be cut off by the self-existent grid. Okay. So the interesting thing is that in the region where the value of the integral is finite, it turns out that the grid is relatively flat, which means that basically even naive Monte Carlo would work reasonably well, provided we know very, very precisely where the function is non-zero. So if we knew where the function is non-zero, the grid is relatively linear inside that. But of course, these limits are hard to find analytically. Okay, so now we can increase this FCT to 1, for example, and now we're going to make slightly more function evaluations. Actually, we're going to make them 10 million, I think. 1, 2, 3, 4, 5, 6, yeah, 10 million. And we see that we converge. Of course, the convergence is slightly slower, but we converge to pretty similar numbers at the end of the day. Yeah, like this. So the final result, the result that you should get, is minus 0.90983. I think these 3 digits are correct. 983. This is the correct value for this particular Q. And that would be sufficient for the homework. Now, the optional part of the homework, which I gave, that's also something that I'm going to solve here, is the following. So everything but optional part of the homework is already solved, isn't it? But let me show you also the solution for the optional part, which is a bit harder. So the idea is that we change the Vegas algorithm so it computes not only the polarization for one value of omega and one Q, like the normal Vegas does, but the advantage that we are developers of the Vegas algorithm, we can tweak the algorithm in such a way that it works for lots of omegas, as many omegas as you want. That's the big advantage of having your own Vegas algorithm, or being the developer that knows how to change the algorithm. Because if you use one of the libraries, you cannot do that. You have to run Vegas algorithm for every omega. Okay, I don't know how else would you do it. You need to do it for every omega. Now, you have some insight or some idea that this polarization here, polarization function, that the grid which you use for omega is equal to 0 is pretty good for all other omegas. Why? Because by just looking at this function, you see that the function is most singular when omega is equal to 0. It's kind of obvious. When omega is equal to 0, we have a real pole, isn't it? But when omega is non-zero, then the pole is slightly shifted away, but it's not, how can I say, the limits in integration where this is non-zero is taken care of by the Fermi functions, by this numerator, because these Fermi functions cut off the limits, and it's not going to be changed a lot by changing frequency. So therefore, if we get the grid for 0 frequency, we can keep the same grid for every frequency, and the result is going to be pretty reasonable. So of course, the value of the integral should not depend on the grid. Only the efficiency with which we calculate the value will depend on the grid. But again, the idea, physical idea here, is that if you get the grid which can do the 0 frequency integration, then all other frequencies are going to come out reasonable as well. Because just looking at the integral, we see that this is a decent assumption. Okay, so therefore, we are going to evaluate polarization function for all frequencies, or all needed frequencies, like 100 of them, at once. Okay, so NumPy will give you, instead of one-dimensional array, it will give you a two-dimensional array as an output for all frequencies at the same time. But then when we change the grid, we're going to take only the zero frequency. That's the idea. So once more, the idea is the following. So when we evaluate this quantity here, P of omega in Q, okay, we're gonna store this as an array of omega and as an array of all momenta K, isn't it? Yeah, all momenta. So we're going to have a two-dimensional array rather than one-dimensional array. And then, of course, all these quantities here are going to be arrays as well. So Fw is going to be array of omega. So Fw is going to be array of omega. And Fw square is going to be array of omega. And all these quantities that we have in cumulants, all these things are going to be arrays. Okay. Now, the only thing that will not be array is these grids. The grids will depend only on Fw square of zero frequency. Okay, that's the idea. And let me first show you how the algorithm works. Before I go through the algorithm, I'm going to just evaluate it and show how it works. And then I'm going to go through and explain step by step. So you've seen before how fast was the algorithm for 1 point. So now we have, I think, 10 million steps. Okay, and so the speed with which we were doing 1 point and the speed with which we are doing now 100 points. So now frequency is linear mesh with 100 points. You see that this speed is not 100 times slower, but it's maybe a factor of 2 slower. It's actually pretty fast. So yeah, so basically 11 and 13, 11, 12, and 13. 13, okay? So this speed is maybe a factor of 2 slower compared to having just one frequency, okay? But we have hundreds of frequencies. And now if we plot the polarization as a function of momentum, because now we have an array cum average real divided by NF and cum average imaginary. So I'm plotting here the output, the real part of the output and imaginary part of the output. Actually I'm plotting this with error bars. And as a function of omega, you see that the error bars are tiny. Basically, you see this just as a line because the error bars are so small that you basically don't see it. Yeah, we got the entire function in one run. Okay, not only one value. So before we were calculating one single value here, we got now the entire function in one run. And actually, the analytic result exists for zero temperature. And if you plot it on top of this, you will see that it's basically 1-to-1. And if you remember from before, the value at 0 is supposed to be minus 0.083. We got also the value at 0 correct. And the grid looks more or less the same as before. The only difference now is that instead of calculating only one integral, we are calculating 100 integrals at the same time. So that's very important. We managed to get lots of integrals with the same run at the same time very efficiently. Okay, so how did we do that? What's the trick? Several things. One, yeah, we start here. So one is that we are going to redefine the Slingheart function. So Slingheart function before was returning value when you have one single frequency. Now the frequency becomes an array. it's actually a very small modification. So when we define the class Slingheart, we give as an input frequency omega, which is allowed to be an array. And then we just remember that omega is equal to self omega. So up to now, as far as I can see, there is no change, because working with arrays or with numbers at this point doesn't matter. But the difference is here. So when we allocate an array for the result, we need to make sure that this is not one-dimensional array, but two-dimensional array of complex numbers. In particular, we're going to choose that the first dimension is the dimension for the frequency, and the second dimension is dimension for the batch of random numbers. So once more, the only difference here is that the return value is going to be two-dimensional, with the first dimension being frequency. Okay, that's all. And then the Slingheart inside is going to be similarly modified in the sense that we are gonna evaluate this function for all frequencies at the same time. So here omega is an array of frequencies, and therefore this quantity is an entire array for all the frequencies. So when we evaluate this, we evaluate for all the frequencies at the same time, entire array, and then we set it properly into the result, isn't it? So we are iterating here over the batch of random numbers. I is the index for the random number, and then this first index in the results is actually index for frequency, and we set the entire array simultaneously into the reserved memory, and then we return this. So the modification of this class is relatively simple or pretty straightforward. The only difference is that we, instead of returning one-dimensional array in the batch size, we are returning two-dimensional array with the batch size, frequency times the batch size. Now, in order to test this, we're going to do the same as before. We are going to first create a small array of omegas, let's say from 0 to Fermi energy 10 points. I mean, eventually we're going to work with 100 points, but right now we just create 10 points for test. Then we initialize this Slingheart class in which the input is this array omega, and the rest, Q, K, F, T, and broad, and so on. Then we define four random momenta, each of them is three-dimensional, of course, and then the result is supposed to have shape of omega times x, isn't it? So let's say y is LH2, and then we print let's say shape of y. No, actually this is supposed to be y shape, and then we do y, let's say. Okay, so we see that the shape of the y is indeed 10 by 4, 10 because of the frequency, and 4 because of the because we put here a batch size of 4. Okay, so this works correctly in the sense that it gives it returns the entire array of random numbers for all the frequencies. Now, the class that we do need to change now is cumulants. The cumulants before were just numbers. So all these averages were just numbers. Right now, we need to work with an arrays, because all these averages are going to be arrays in frequency. So when we define the cumulants, it's going to be a new class, cumulants W. I call it cumulants W because it works with frequencies. When we initialize this, we need to give an array. We need to give the frequency array so that we know how big is the dimension. So n omega is now the size of the frequency array. And then we initialize all these sums to correct shape of the arrays. And we need to know whether they're real or complex. So now let's go through all these quantities, whether they need to be real or complex. We discussed before that the value of the function is going to be complex, but the square of the value of the function is going to be real. Sigma square is going to be real, but f divided by sigma square is going to be complex, and I best is going to be complex, and sigma is going to be real. So therefore, all these quantities need to be properly defined. So self-sum is the one that contains the average of the function. That clearly has to be complex, and the size of the array is as many as we have frequencies. Then f square is real array. Average is this I best, is the best estimation for the value of the function. This is complex as well. The error is the square root of sigma square, which is sigma. This has to be real. Then chi square has to be real. Then the rest of the weight sum is basically 1 over sigma square, which again has to be real, and so on and so forth. So there are some of them complex, some of them real. Okay, so this is generalized of the previous cumulants. And then finally, Vega step 5 is similar to Vega step 4, but it works with an entire array of frequencies. So how is it changed compared to previous step Vegas 4? So let's see. As far as I remember, all this part here, the input is the same. All this part up to here is the same. Then the difference has to do with evaluating the function. I guess up to here, there is no difference. As far as I remember, there is no difference whatsoever. Yeah, because fx bin is projection, but it's still just two-dimensional array, and the grids are exactly the same as before, so there is no difference. However, when you evaluate the function, we will get now array with one more dimension. It's going to depend on frequency. Okay, so therefore we need to remember that fx now is not a one-dimensional array, is actually a two-dimensional array. So fx returns something that's on frequency and n. Okay, so it's a two-dimensional array. Now, here is the crucial point, the crucial step. We have f, which is a two-dimensional array of omega and I. So you can call this I. Basically, it's a batch size. And we need to multiply this with weight, which depends only on I, doesn't depend on frequency. So weight depends only on the batch because it's calculated in exactly the same way as before. And then we want to have a function W fun, which is a two-dimensional array of omega and I. So how do we achieve that? Well, in C, of course, we will write a double loop, isn't it? W of omega and I times W times Wi is V fun of omega I. But in Python, we can write this simply just like this product, and it works. Okay. Now, I didn't know at the beginning how exactly do I need to do it, and I had to read the documentation of NumPy, how NumPy behaves. Okay, so to remember, or basically you have to go and read the documentation of NumPy. But the idea is that if you have a two-dimensional array such as B, I, J, and if you multiply this with, let's say, C, J, then it turns out that what NumPy does is creates a two-dimensional array which contains indices A, I, J. Okay, so this is how NumPy array works. Okay, if B is a two-dimensional array and C is the one-dimensional array, and as long as this the dimension of the second index works, then there is going to be no error, and the result is going to be obtained in this way. Aij is Bij times Cj, okay? Again, in order to understand this, you need to read the documentation of NumPy, and indeed this works. So because of this beautiful way the NumPy works, we can then construct this value of the function simply by just writing times, okay? So in some sense, the code hasn't been changed. Or basically, I just I put fx first on the left-hand side and vgh on the right-hand side. I think this is essential. Okay, so this is easy. Now, when we calculate the average value of the function, this we need to sum over all. We need to sum over all random numbers in a batch. Sum over all I. V fun of omega and I, okay? So we need to carry out this sum. Now, how do we do that? Basically, we need to sum over the second dimension of this quantity. So V fun is two-dimensional array, and we need to sum over the second dimension only, not over the first dimension. So now, thanks God, NumPy already comes to the rescue, because it turns out that in addition to simple routine sum, which would sum over all dimensions, we also have a routine in which we can specify over which axis we want to sum. And if we set that axis is equal to 1, that means that it's going to be sum over the second dimension only. The first dimension is going to be kept, okay? So basically, it turns out this cum sum now becomes one-dimensional array of omegas, just like what we expect. Now, a few other things. Now, V fun is two-dimensional array of omega and I. Then we conjugate the same thing to calculate the square. And here I'm multiplying with all n samples so that actually I have exactly f square. We discussed before that without multiplying with n here, we don't get exactly f square, but right now we have exactly f square when we multiply with this n. And this again is two-dimensional array because that's how NumPy works. So V fun 2 is now a two-dimensional array. And now if I want to get a two-dimensional array of f square of omega, which is sum over all the batch size, over all the values in the batch size, again, I do the sum over x is 1. And I will take here the real part because V fun is, we take the absolute square before. So basically, this should be a real quantity. And then this is the crucial step, the very crucial step, is that when I set this f-twiddle functions, the f-twiddle functions which are going to be used for new grid, I take only the zero frequency value of this V fun 2. Okay, so this is f square. So this quantity V fun 2 is f square, isn't it? It's projection. And before we were giving the entire array to the set fx bin. Right now, instead of giving the entire array, we take the slice that corresponds to zero frequency. That's all. Okay, so otherwise it's exactly the same routine. The only difference is that we give the slice that corresponds to zero frequency. That's the only difference. And then the rest is very straightforward. Actually, it turns out that the code is identical to before. There is no difference. But in reality, of course, it works differently. Why? Well, because, for example, here, this W is 1 over sigma square. Okay, W is 1 over sigma square. And now it's an array in frequency. So why? Because cum s cum is array in frequency, cum sum is array in frequency, and W becomes an array of frequency. But all the equations are identical. There is no change. You just need to remember, okay, now everything is an array of frequency. And as far as I remember, all these things are calculated in exactly the same way as before. The equations look the same, but everything is now an array in frequency. I think that the only difference is that when I print the chi-square, I take chi-square of 0, chi-square of 0, because we just want to print, when we print out, we don't want to print the entire chi-square for every frequency, we just print chi-square for frequency 0. Okay, so that's the only difference. We smoothen the function exactly the same way. We redefine the grid in exactly the same way as before. And well, there is one more little point here. This line, these two lines are different because before we set cum sum is equal to 0 when we reset the partial sum, but now we need to reset the array to 0, not the value to 0. So if you write here cum sum equal to 0, not as an array, it will not work correctly because we are going to create a number after that. But we don't want to create a number. You just need to change the array. You need to nullify the entire array. But to nullify the entire array, this is the way to do it. Okay, so that's the important difference. All the rest is exactly the same as before, no difference. Okay, so and yeah, how does it work? I already showed you before. So with this, I solved the homework, and I hope that you can make the homework in a week. Is this okay? Can you do it? Are you still present? Any question? Ah, there is a, yeah. Please, Brandon, can you ask a question? No.
Oh, no, I wasn't asking a question. I was just thumbs up.
Thumbs up. Oh, thank you. Good. Okay. Any question?